Okay, next we'd like to welcome Sophie Watson. She's a senior data scientist at Red Hat, and she has a presentation, DevOps for Data Science with Kubernetes. And I hope I did not destroy the title of your presentation, Sophie. So
I'm going to call it Kubernetes for the duration of the talk, but I like Kubernetes, and okay. I think it might catch on, to be honest.
Thank you. Well, welcome. The stage is yours.
Thank you so much for having me. So hopefully you can see some alpacas, and I'm going to go ahead and go into full screen, which means I can't actually see you or the chat anymore. So please just do interrupt me, Chris, if something isn't looking quite right. But hopefully you can see my slide right now. So yeah, thanks for the introduction. I'm Sophie. I'm a data scientist at Red Hat. And today I want to talk about how data science and data scientists can really benefit from things that software engineers have been using for quite a while now, namely Kubernetes as a platform and DevOps practices and principles. So we're going to focus on the benefits that they bring to us as machine learning practitioners and data scientists, and we'll see how they fit into our daily workflows. We're going to look at some high-level tools and technologies that are going to help us to benefit from Kubernetes and DevOps practices without having to become Kubernetes experts. And hopefully I'll get a chance to get to some Q&A today, but if I'm unable to answer your question today, please do just reach out on Twitter or email. So I want to start by talking about the machine learning workflow. What do we as data scientists actually do? Now, obviously, this is level setting. I'm not expecting to tell you something you don't already know, but I just want to make sure we're using the same language and we've got this workflow fresh in our minds. So when I'm first tasked with solving a problem, I start by, defining that problem and thinking about what metrics I'm going to use to define success. How will I know when I've done a good job? From there, it's on to data collection or cleaning. We might already be collecting the data. We might have to start. And then this is where the data science really starts, in my opinion. So feature engineering, trying to extract patterns and feature vectors from that data that capture the information about the data that we want to expose with our machine learning model. So we take those feature vectors, we train and tune our model, and we validate it to check that it's performing as well on data it wasn't trained on as it is on the data it was trained on. From there, we're on to model deployment, putting that model into production. And I know that means many different things to many different people. And today we're going to think of it as meaning, exposing a model service as part of an intelligent application that you can interact with. But there's obviously a lot of different levels of production that we see across our work. And once we're in production, we've got to go ahead and do our monitoring and validation, checking those models perform well over time, identifying data drift, changing tastes, changing habits, and potentially update the model. So hopefully this workflow resonates with you. I've talked about it as being a linear and incremental process, but in practice, that's never how it works. So at many stages, you find yourself backtracking, changing decisions you've made at an earlier step, rerunning code, retuning parameter values, re-implementing methods, or trying different models, and so on. And some of this workflow is simply exploratory, but some of these stages lead to code that will eventually run in production as part of a pipeline. So the code we developed for our model deployment, monitoring and validation is going to be more or less directly used in production. The feature engineering stage is going to give us some code for feature extraction that we can use on real data in production to go ahead and extract those important data properties. And the model training leads us to code that we'll use to train that model in production. So those components directly inform our training pipeline, which takes in labeled data, extracts features, and trains and validates our model. And they also inform our production scoring pipeline. Ultimately, I'm thinking that we want something we can put into production that extracts feature vectors from more or less raw data, makes predictions, tracks metrics about our model so that we have an idea when it's going wrong, and archives that data we saw and the predictions we made so that we can explain ourselves later. So if we go back to this workflow, I think that the boxes representing each of these stages are in practice not really the hard bit. As a data scientist, that's where I want to be working. I want to be spending my time training a model, doing feature engineering, trying to extract business value from data. But it often feels like when I'm going through this workflow that the diagram should look much more like this. The bulk of my time seems to be spent between these stages or repeating stages. So for example, when I go to get started, when I've got my data and I want to start feature engineering and model training, I need to set up an environment, and that can be a headache, package management and so on. And then all of a sudden I realize when I'm training my model, I don't have enough memory on my local machine. So I want to run it in the cloud, and then back to environment setup somewhere else and package management again. And once I've trained my model, I want to connect it to some different data to validate it. Connecting to data sources can always be a headache. And arguably putting that model into production is going to be the biggest headache of them all. And outside of that pipeline as well, the machine learning pipeline, we've got even more problems. So we put these pipelines into production as part of components of larger software systems that use machine learning to solve real business problems. And these systems are even more complicated than just those pipelines themselves. Machine learning is just a small part of that system, but it can make everything so much more difficult. Now, if this diagram looks familiar, it's because I'm borrowing it from an excellent paper, Hidden Technical Debt in Machine Learning Systems. If you haven't read this paper, I think you must. So it starts with the premise that machine learning techniques are easy to develop, but machine learning systems are hard to maintain because they've got so many moving parts. And as a whole, these other parts represent much more engineering effort than that machine learning code itself. But it's the dependencies between the machine learning code and the rest of the wider system that can make this whole application even more complicated and can really exacerbate any bad engineering properties of our system in ways that is really difficult to identify. So the focus of this talk today is going to be everything around the data science. How can we make everything around that data science workflow work well so that we as practitioners can focus on our data science? So today we're going to see what Kubernetes and DevOps practices do to make it easier to build these systems, to execute these workflows, and to allow us to get back to focusing on that data science rather than managing infrastructure or fighting with model dependencies. And we'll also see a demo or two and introduce some high-level tools and communities that you should be aware of if you want to reap these benefits. Okay, so in order to talk about Kubernetes, which we'll get to in a moment, we need to start with containers. And a container is a Linux process that uses namespacing and resource quotas to provide lightweight isolation. Simple, right? So as a data scientist, I hate that definition. And for the purpose of this talk, I think we can think of a container as a nicely self-contained parcel that contains everything that you need to run an application or a process. So we're just thinking containers are parcels. Now, Kubernetes is a container platform. It builds applications out of lots of containers. But first, we need to build those containers themselves. So what's in a container? Well, these container images are made up of immutable layers containing a base image that provides any minimal essential functionality, any library dependencies, and then the code for the application itself. And from a machine learning viewpoint, anything which is immutable is much more likely to be reproducible. If you know what you're running and what you trained it on, what data you trained it on, you can get the same results in the future. And this enables you to make comparisons, for example, between two models, whilst keeping everything else constant. It also enables you to answer uncomfortable questions from regulators. So, for example, why did you decline my mortgage? Why did you delete my legitimate social media posts? And we can combine multiple containerized processes to create an application. So each process is commonly called a microservice, and these are stateless. They communicate with each other through well-defined interfaces, but they can only talk to each other because we've set up network routes. They can't access the outside world unless we explicitly let them. And the lovely thing about microservice architectures is how easy it is to scale these applications. So we can scale them up on the same machine, or we can scale them out running on different machines. And this scaling is possible because they don't share any state without communicating with each other. Now, commonly when you're running stuff in real life, you'll find that part of your application is a bottleneck, slowing down the application as a whole. And with stateless microservices, this is really easily solved. You can just run multiple copies of that microservice that was slowing down the whole process behind a load balancing proxy. So if we think about the machine learning setting, you often get high throughput when you're trying to do model scoring to make those predictions. If you're running a social network, suppose you've got a spam classifier or spam classification model running there as a service, and say it takes 5 milliseconds to score one social media post, but you need to be able to score more than 200 a second. So in that case, you can just roll out multiple copies of your model to do the scoring, thereby preventing that bottleneck. And microservices also make it easier to roll out updated services. So if I develop a new model for scoring a social media post as spam or legitimate, I don't want to immediately roll it out to millions of social media users. Instead, I'd use maybe 0.1% of all posts, check it's working, and increase that percentage as my confidence in the model increases. So this makes transitions to new versions of services so seamless. You don't need to bring down the whole system to upgrade a component. You can just upgrade it whilst it's running. So that's some of the things that container platforms and Kubernetes brings to the table. And another thing is a simple way to maintain and set up deployments. So by specifying a declarative deployment configuration, which describes how your services should be connected together, rather than giving a step-by-step deployment recipe, container platforms are able to set up and maintain your deployment for you anywhere, be it, on your personal laptop, in the public cloud, or behind your company's firewall. And for machine learning, these declarative app configurations make it really easy to test different parameters or different approaches through reproducible environments whilst keeping everything else constant. Okay, so that's some of the ways that Kubernetes and containers offer capabilities to, make these distributed applications and machine learning systems easier to manage. But in general, we as data scientists shouldn't have to become Kubernetes experts in order to reap these benefits. So let's talk about some DevOps tools, continuous integration and continuous deployment, and some higher level abstractions that can really help us here. At Red Hat, we've been big fans of doing machine learning in containers for a long time, which perhaps isn't surprising given that we're Red Hat, but this has started to get more and more popular over the last couple of years. And we've started to see an increasing number of articles that show data scientists how to get started with containers and Kubernetes. But all of these articles sort of start by diving into the details of the infrastructure. So here's a container recipe, here's a YAML file, here's a litany of shell commands. And we really don't think that data scientists and machine learning practitioners want to have to care about their infrastructure just to get their jobs done. So we want to instead focus on these higher level advantages of Kubernetes for machine learning. How can we entice data scientists to want to use Kubernetes? Well, a huge issue for me as a data scientist that Kubernetes solves out of the box is portability. So I like to work on my own laptop, but obviously I cannot get access to that sensitive data. I'm restricted by the speed of my laptop's CPU, and my laptop sadly has less storage than I'd like it to, so I'm always working with a reduced set of data. And when I'm training my machine learning models, obviously that's math heavy and hardware acceleration can really help. But laptops aren't as powerful as workstations or servers. I've got a GPU in my laptop here, but it seems to speed up editing movies, but it doesn't do anything for model training. So Kubernetes enables me to access better hardware. I can scale out training for different models and scale up with GPUs. I can access more storage and private or sensitive data. And I can do all this in a self-service environment. So anybody who can create a Kubernetes resource can deploy a notebook environment or a specialized compute cluster or any other essential infrastructure services without having to file a ticket with IT or without having to take a corporate card to the public cloud. Now, reproducible environments are one thing, but reproducible research is another. And data scientists like to do a lot of work in notebooks. I hope that's not controversial. I love working in Jupyter notebooks. They're really powerful for experimentation, but they're not a very good durable artifact. One of my top skills is sending somebody else a Jupyter notebook that she is unable to run, simply because that notebook is dependent on my environment, the files I had available, what order I ran the cells in, and so on. So we want to, be able to get around this and be able to effectively reproduce the work that we do and share it with others. And mybinder.org is a really cool service that makes notebooks reproducible using Kubernetes. So it takes in a Git repository full of Jupyter notebooks. It builds these into containers for you and deploys these containers in a Kubernetes cluster that you can access. This is a public hosted service, so you can go and try it out right now. And it's also open source, so you can run it on-prem in your own data center. So just by putting a notebook in a Git repo, you can share it with anyone in the world and have it be totally reproducible. Now, if you're using Binder, you're already using some DevOps practices. This idea that we can obtain repeatable deployments again and again is so beneficial. And Binder was this, it's a service, it turns code into services, but we can really generalize this idea by looking at OpenShift source to image builds. So OpenShift is Red Hat's Kubernetes platform. And source to image builds provide a framework to make services that know how to turn code into services. So basically, the idea is that we have a builder image that knows how to turn a Git repository of something, be that source code or whatever, into a container image that we can run as a service on Kubernetes. And the nice thing as a data scientist about source to image is that I can use it without being a packaging expert. So I'm going to use a builder image that one of my colleagues, Graham, made. This knows how to take a repository of notebooks and turn them into a notebook server container image. And that gives me the same functionality as Binder without really doing any real work myself. So I can do this in a single command line argument to deploy that reproducible notebook container on my laptop or anywhere else. So this is the image that Graham made. It knows how to take a repo of notebooks and turn them into a reproducible container. This is my repo of notebooks that I want to pass in. And here's some super secret password. And that's all it takes in order to get that notebook service up and running. And you should definitely go and try that out for yourself. But source to image is more general than just building applications or notebook servers through CI and CD. So any task that involves generating a container image from source files can be implemented by one of these. For example, the Selden project for model serving has a source to image builder to turn serialized Python objects into model services. But next up, we'll see that these builders can do something much more involved. What I'm going to show you now is a source to image builder that operates on Jupyter notebooks and trains a model creating a service. So this source to image builder loads a Git repository that contains Jupyter notebooks. It post-processes that notebook to identify all of its dependencies. And it then post-processes the notebook to extract the code, because notebooks are a mix of code and, literate. human readable language, and it runs that code, runs the script that trains the model, and finally creates a REST endpoint to serve that model. So if we go back to the workflow, we're thinking about a notebook for each of these two stages. We're running them repeatedly and ending up with a model deployment. So let's have a look at this. So I've developed a technique for the feature engineering part of my model of my machine learning pipeline in this notebook here. And this is actually working on fake social media data. So we're trying to identify things as spam or legitimate. So that was one notebook for the feature engineering. And I have another notebook here for the model training. I'm just training a logistic regression model. And you can see that it just looks like a normal Jupyter notebook. There's nothing fancy going on there that you wouldn't see. There's no knowledge of where this is running. So if we go over to the OpenShift console, we can go ahead and just insert this new pipeline that knows how to build us our container, our model service from that those notebooks. So we pass in the Git repo, we pass in a list of the notebooks names, because there's a lot of notebooks in that Git repo. I only want it to run those ones. And we can go and click create. And we are going to tail the logs here. But what will happen is that we get a pipeline service that is up and running. So this is a really simple and powerful way to go from a notebook to a model service that you can interact with. And actually, we're going to interact with it through just another Jupyter notebook. So you can see you can make predictions, and that's passing them to that model service. So I could give that exposed model service address to an application developer on my team or another data scientist, and they can have a go with my model, mess around, see what needs to be done before we can put it into production. Now, once we've got that model service and models in production, we need to monitor their performance. So we know that data can drift over time. And of course, we don't always have a way to get the ground truth for a model in every case. So we can't directly track a model's predicted performance over time. But there's these other metrics our model service could publish that give us a reasonable proxy for data drift. So for example, what does the distribution of predictions look like? And if one of these changes substantially over time, it's a safe bet that the data has drifted. So let's revisit that spam classification pipeline demo and see this in action. So we have here our get metrics function, and you can see all the standard Python metrics that are exposed like normal. But the ones that we're interested in today are these custom pipeline prediction total metrics. So they tell you how many predictions of each type your model has made. And we can actually just use inside OpenShift, a native Prometheus time series visualizing tool to have a look and visualize when they change. So we just ran a couple of experiments there, and you can see that there's changed distribution of predictions significantly. So we go back and see what had happened and maybe retrain that model. And this is all really easy and simple with Kubernetes. And we can also use predictive performance metrics to compare these models that might be running simultaneously. So like we said earlier, we might have multiple copies of a model running, or we might have two different models running. And we can gradually, decide to roll out a new model service by looking at these metrics and monitoring the performance over time. Okay, so in that whistle-stop tour, I hope I've convinced you that you should be running your machine learning workloads on Kubernetes and getting to grips with some DevOps practices whilst you're at it. And the tools that we've seen today can be used by data scientists to make work more repeatable. So a couple of projects I want to tell you about before I wrap. One is the Open Data Hub, which is an open source project out of the CTO's office here at Red Hat, and it's a reference architecture for machine learning discovery in the cloud on a completely open source stack. Now, Open Data Hub is downstream to Kubeflow, if you've heard of the Kubeflow project. So it leverages Kubeflow manifests and operators and extends it to cover a wider range of components. And we also, work with the Kubeflow team to verify Kubeflow on OpenShift and contribute fixes back. So you should definitely have a look at that. When we think of machine learning going into production as part of an application, these applications are built by cross-functional teams that all have different priorities and different concerns. And so there's components in the Open Data Hub that are really beneficial to each of those personas. Projects like Strimzy for managing streaming data, Argo and Kubeflow pipelines for defining your machine learning pipelines, and things like Spark for scale-out computing. Okay, so with that, what have we seen today? Well, we started by level setting on the machine learning workflow, just to really remind ourselves how important repeatability is and what the barriers to getting work done are. From there, we introduced containers. So we saw that containers can be used to isolate processes, and then Kubernetes as a container platform can orchestrate, manage, and distribute those components into applications that are made of containerized microservices. We've got source to image builds that are providing a really flexible way to benefit from the work of packaging experts without having to become one yourself. And we talked about the My Binder service, which you should definitely check out if you're aiming to share Jupyter notebooks. Finally, we briefly touched on ODH and its components on top of OpenShift to do machine learning. So with that, I'm going to stop there. Thank you so much for spending your afternoon or evening with me, depending on where you are. And there may be time for questions, or maybe I'll just get to them in the chat. Thanks.
Yes, thank you, Sophie. So we have a little bit of time. We're up against a 5-minute break, but there's a question here in the chat room. Are Binder and OpenShift interchangeable, as in they perform the same type of function for DS workflow?
Okay, good question. So Binder is just doing that one thing, which is the repeatable notebook builds. So you can use Binder to take a Git repo that contains a notebook and repeatably spin up an environment in which that notebook will run and share it with people. OpenShift itself as a platform has capabilities to support that, but OpenShift is really a much bigger service. So it manages many more components of the machine learning workflow. In OpenShift, you can spin up, a Jupyter Hub instance, for example, and train a model. You can then serve that model with Selden inside OpenShift. I hope that answers your question, but I'm happy to talk offline more about that if I can be helpful.